Hi, my name is Eric Ortiz. I'm here with my team, Enrique and Mark. We're here to talk to you about the ischemic stroke smart aspiration tubing brought to you by MEng-MIVI Neuroscience. So our motivation for this project was really dawned by the stroke cases of the US. Nearly 800,000 people per year get a stroke and suffer from the ailments following that stroke. It's been proven that the time of extraction is very important as more blood flow to the brain gets blocked, creating more problems down the road.
Here we have our mission statement. Our mission statement is quite simple. We want to save as many lives as possible by using our skills as engineers. With this project, we provide the physicians a potential tool to illustrate more information of what is occurring in the body. Our main goal is to provide a simple yet elegant solution for the physician when tasked with removing blood clots from a stroke victim. With this, we have our objective. We want to develop and apply an algorithm that will provide useful information and insight to physicians carrying out thrombectomies. We will implement a clear, decisive interface that can easily be understood by anyone.
The first point that we're surpassing others is that our price. So we're aiming at a final manufacturer cost of $100, which is affordable for most of families. Also, we're having better safety because we're going to have algorithm telling the parameter of the clots so that the physicians can see how that is going on.
With this, we have prototype 1 and prototype 2 and 3. The prototype 1, we only have 2 hertz. And you can see the pendotech monitor, which is essentially where everything happens, and you have a big pump at the end of it. The claw catcher, the guide catheter, the pressure sensor, and flow sensor. We move on to prototype 2, which has a solenoid valve, a Nordic Bluetooth system, a flow sensor, and a pressure sensor. We were able to do 10 hertz to 50 hertz with these prototypes. Prototype 2 had a broken flow sensor, and we removed the solenoid valve, and that made us proceed to prototype 3, which had no solenoid valve, and our flow sensor was up and working.
So this is our trial flow chart. First of all, we're going to start with opening the vacuum. Then we're going to collect our data for 30 seconds, like doing water aspiration to see whether the system is working correctly or not. Then we'll start our aspiration. If the clot is aspirated, we'll do the collect until the clot goes through the system. But however, if it is clogged, we'll keep data collecting for a minute. Then we're going to get the clot out of the system. And finally, we're going to stop collecting data. Here's the conditions of our identification. The first 3 is the closest to the reality, which is the clot aspiration, cord clot, and air leak. Also, we're doing some other conditions as comparison, including some aspiration, direct clot aspiration, King catheters, also the air leak, clot aspiration, and aspirating blood.
Here we have the prototype 3 video and setup. On the left is the video of the experiment being carried out, and on the right is the plot of the actual experiment. On the right, we have water flowing through the system, and at roughly 45 seconds, we come into contact with the clot. Then, at roughly 68 seconds of gathering data, we then pull the clot out of the system, and then disengage it from the system altogether, and let water flow back through the system. On the left, we have what prototype 1 data look like. As you can see, it's only at 2 hertz, meaning there's only 2 readings per second, which does not have enough data to really illustrate what's going on within the system. On the right, we have a little bit more detailed data of what's going on during a clot aspiration. Going from left to right, we have that water was flowing through the system, the catheter came into contact with the clot then got aspirated, and then eventually went through the catheter system and returned back to normal. As you can see, the time frame, it took many seconds to go through the system and not enough fidelity to really be an accurate model.
Here we have our data from prototype 2. As you can tell, we have two figures. Figure 5 has very sporadic data, but both of them have a very shared common one, with flow being very sporadic due to a broken flow sensor. But as you can tell in figure 6, our pressure, you can tell that when it meets the clot around 25 seconds, the pressure increases and then decreases after the clot goes all the way through. In prototype 3, we can see that at 50 Hertz, we collect a lot more data points, and you can see a lot more prominent changes. So here we have normal versus direct clots. We did this comparison due to physicians being able to obtain clots in very different ways. One is when they turn on the vacuum right when they meet the clot, and the other is they make their way to the clot with the vacuum already on. As you can tell, both direct clots aspirate and begin aspirating this clot around 18 seconds or around 20 seconds as well. For the two normal ones, they get fully aspirated around 30 to 35 seconds and then go back to normal after that.
On the right, we have an overlay of a cork, a thumb, aspiration, and a kinked catheter. This is meant to differentiate and discern what's going on within any given corked-like system occurrence, such that looking from left to right, we see that water flows through the system. It is then come into contact to which condition behaves, such that it is either kinked, the thumb is in contact, or it is corked with a clot, and it goes to a sudden value of whatever it behaves at, such that it is almost approaching a vacuum. And then once it becomes released, we see a sudden change in slope. This area allows us to differentiate between the corked, thumb, and kinked.
Here we have our simple code that's used for the algorithm. So you first start by choosing the catheter size that you want. Then you do access the flow and pressures data. This data is actually user inputted, as you can tell in the code. And then you begin your aspiration. Then you get told between aspirating blood, a clot corked, or an air leak, as you can tell from the video. From there, the physician will know what to do. We chose these three conditions due to the most common ones that a physician might see through a thrombectomy.
When it comes to our future endeavors, first of all, we're going to apply machine learning. If we got enough data to train our model, to get it more like precise. Also, we're going to compute amount of air leak and integrate live data acquisition. Also, we're doing with power spectrum identifiers. If you see the figure on the right, there's a spike on the 10 Hertz. So what we're doing in the future is like we're going to put different spikes for different conditions so that we can like identify different conditions easier.
Thank you.
Thank you.